So now we get into the meat and potatoes of this whole 4-stage process. We'll focus on each stage one at a time. The first step is goal definition and scoping. Very important. It's at this first step the purpose of the study is determined. Why are we doing this? Why are we doing a life cycle analysis? Maybe because there's been a perception maybe in the industry, in the society, that our products are very environment unfriendly. Our business practices have long been criticized. Or it just may be that we aren't, we are doing quite well, but we want to see if we can improve our profit margin. Let's look at a commercial reason, right? If you consume less energy, less material, well, that improves your... So what is your purpose in doing an LCA? It can help you do both. And the next thing is to define the scope, how broad, how narrow, etc. And lastly, some sense of how we're going to use the results of the LCA in decision making. So these things have to be established early on. So this will prompt you to ask, what kind of information do I need? The next question is, how accurate do they need to be? These are very important considerations. You can get idealistic and seek all kinds of information. You have to ask yourself, is this information really going to help me with what I'm trying to seek? And then how accurate do things need to be? It's like buying a home, right? If you're comparing two homes, they are both in the neighborhood of $250,000. What does it matter if one is priced $50 more than the other? So how accurate, because you can get incredibly accurate, that takes a lot of time and painstaking work. Is it worth the effort? And the last step is how the results should be interpreted and displayed so that it's useful for decision makers. Not every decision maker is an engineer. We have people from different walks of life. We need to present the findings in a way that the whole group or team can find useful. The next step in goal definition is to try to identify questions that decision makers may care about, because that can help you bring some more focus to this process. It can also help define your study's parameters. We'll just go over a couple of these. The first thing is, what is the impact that to particular interest groups? It could be your investors, it could be your immediate neighboring society. So what is it that's important to them? Because that is whom we are trying to talk to. The next thing is, you may want to know which product in your product line or which process step causes the most or the least impact. So these are some questions. The answers to these questions will help you determine the study parameters. We're going to talk about some of these parameters. The first step is what is called a functional unit. Very important in a LCA, and it's important that everybody associated with the study have a clear and consistent definition of what the functional unit is. So it has to be clearly defined. It's basically a measure of the function that you're providing in the product or service. It's a measure of the function. It is a common reference to which all the inputs and outputs can be related. When we compare two disparate solutions to a problem, it's easier to compare these two disparate systems if we have a common reference, and that's what the functional unit is. Let me give you an example. Suppose we're talking about spraying automobile body panels. You could have a manual mechanical process of applying paint with a brush manually, or you could have a robotic arm that's spray painting. Two very different processes. One is very time intensive, laborious, and another is automated. It may seem like comparing apples to oranges. So we can bring both to a common ground or reference by specifying a functional unit. I might specify my functional unit is a unit area of surface that needs to be protected. What's a unit area? It's a square feet, 1 by 1. So I'm going to look at a 1 by 1 square feet of surface that needs to be painted in order to protect it from maybe corrosion or what have you. And this protection is to be provided for a 10-year period. Now I can compare hand painted versus spray painted by robotic arm on a common footing. Likewise, if you're comparing different beverages, whether it's a cola or different kinds of cola, if you specify an 8-ounce aluminum can, then that's a functional unit that makes it. Or you're talking about trucks distributing gasoline. So we talk about a truckload of a certain size, then we can compare different products. So functional unit is therefore very important, has to be decided early on, and everybody in the study should have the same or consistent definition. The next thing is system boundaries. You remember the black box we talked about earlier? Those system boundaries have to be carefully set. The broader the boundary, the more the time, the more tedious and the more expensive things will be. The smaller the boundary, the more accurate your findings will be, but the question is, do you have all of the information you need? And is it generalizable? So system boundaries also have to be set early on. It is somewhat subjective, but nonetheless, because it's subjective, it's not unimportant. It has to be very deliberately and carefully chosen. So there are many ways of specifying the boundary. The first and the most common way and the classic way is that the boundary is established between the technological system and nature. That is your typical cradle to grave. Cradle is the nature from which you extract stuff. Then you have all of your processes from mining to smelting to manufacture, delivery, transportation, use, and then at the other end you have the grave where the material is either recycled or just sent to a dump. So that's the boundary between technological system and the grave. Now this kind of boundary sometimes can be too big, but the most cherished boundary typically. Other boundaries is dependent on what we are talking about. Sometimes we use a geographical or spatial horizon based boundary. It depends on how far or how much or what are the scope of the impact of the product or process. And so in some cases the impact is felt over a small area, sometimes over a moderate and sometimes large. As a case in point, if you're talking about a local manufacturing plant in San Marcos and the exhaust is sending out soot, now the soot is an environmental impact, but it very likely may not even impact people in San Antonio or Austin. It's probably felt a few kilometers around the plant. So that's your geographic or spatial horizon we're talking about. Because if you're measuring, taking data, analysts need to know, are they supposed to look over the entire state or all of Central Texas or just the city of San Marcos? It's sometimes, if you're talking about processes releasing oxides of sulfur and nitrogen, automobile emissions do that, other processes can, they can result in acid rain that can impact an area of several hundreds of kilometers. The third kind is one where the process may release large amounts of greenhouse gases into the atmosphere with the potential for global warming. Well, that's not just limited to Central Texas or even the US or just even North America. It may be much more wider. So you need to ask yourself, if you choose a global horizon for a local problem like soot from a plant, it's meaningless because you're collecting data you don't need. It's a futile attempt. So this has to be carefully thought out. Another thing is the time horizon. Boundaries is not only limited by space but also time. Sometimes environmental impacts are short lasting. Sometimes they're very long lasting. So we need to determine that too. For example, if we are talking about smog, like you might see in LA or some big city, right? Smog is caused by activity as also atmospheric and weather conditions, which change over a week, maybe even earlier in a couple of days. So smog may have a time frame of a couple of days, a week at best. Other events where we are building a big bridge over a river, well, that's going to disrupt the ecology considerably, and its impact, it may even change the course of the river a little bit and can impact for many months, many years perhaps. And again, if it is something we are doing with greenhouse gases in a significant way, increasing it, those effects can be felt for many, many years. So, you have to decide that too, the time horizon in addition to space. And the last thing is, sometimes cradle to grave may be too much. So you may decide a boundary between your current life cycle that you're interested in and related life cycles that precede and follow. For example, if I'm talking about manufacture of steel sheet, then we may choose, because we need quick data, to ignore a previous cycle, which is from mining all the way to smelting and production of billets or slabs of steel, which then will enter our system to be rolled into sheets. And then those sheets, once they are shipped from our plant, will go to an automotive plant where they are formed into body panels. But I may choose to set a boundary between the first life cycle, which is creating those steel slabs from nature, starting off with the ore. And on this side, I may close the gate at the point where I ship out my sheet steel, because I have no control over how those sheets will be used by different consumers. So these are different ways of specifying your system boundaries. Some typical system boundaries have some bus names, and so they would talk about cradle to grave. We already covered that. That's the cherished or the most ideal one. Sometimes can be too tedious and expensive in terms of man hours and cost. Then you have the cradle to gate. Cradle to gate, right? Gate refers to the gate at a manufacturing plant where things are shipped out. So you're stopping your analysis right there. These sheet rolls, steel sheet rolls, are a perfect example. We may, if I'm a manufacturer of steel sheet rolls, I may begin my analysis from the cradle, mining iron ore, making pig iron, making steel blooms and billets, rolling them to produce sheet steel, and I stop it right there. Because automotive manufacturers do something to it. It could be that somebody is making appliances like Whirlpool or Maytag, which are making dishwashers and clothes washers and dryers and so forth. So bottom line, once the sheet steel leaves my plant, I have no control over what happens to it next. So it's a cradle to gate. The next thing is gate to grave, and as an example, I have automobiles, right? So if I'm interested in knowing what happens, I could take the approach that I want to see how a car or different kinds of cars perform from the point they leave Ford to the end of their life. I may want to know, because they could take entirely different kinds of life cycles. For example, in the US, we have certain laws about yearly inspection, and about we have fairly stringent emission laws. In other parts of the world, there may not be such stringent inspection or emission laws, and so Ford Motor Company has no control over that. So if I'm interested in knowing how they fare in different parts, I may choose to go from gate to grave, because from cradle to gate maybe they have a common path. Thereafter they have divergent paths. I could also talk about gate to gate. This would be in the case of microchips like Intel, right? Intel makes different Motorola too, makes different kinds of chips. Some are used in your computers, some maybe in your electronic watches, Fitbit, or in your automobile. So there are different uses. But Intel may choose to do its life cycle analysis from the point where semiconducting material like silicon ingots or silicon wafers are shipped to Intel from a supplier, say in Taiwan. There's a whole life cycle from where sand is processed through many steps to make electronically pure silicon, and an ingot, which is like a big thick bar of silicon, is sliced like deli meat to produce individual wafers. They may say that's outside our plant, we won't include that. We start from when you ship your boxes of silicon wafers. We then will include everything we do to those silicon wafers, from cleaning to various layering processes, etching, and so forth, and ending in packaging of those chips. But we won't include what happens after we ship the chips out, because I could be shipping my chip to Ford Motor Company that's putting it in electronic systems in a car. I could be shipping it to Raytheon, who's working for US Defense on a missile, on Tomahawk missile. Or this could go to Hewlett Packard, which is making various printers and plotters. I have no way of telling how those chips. So it's gate to gate. The first gate begins where those wafers enter Intel. The second gate begins or ends where those chips leave Intel to different consumers. And the last commonly used is called well to wheel. This is often done with companies that make fuels for automobiles. Whether it's Exxon, Mobil, or whatever, right? They can only deal with that part of the life cycle from where they have their own offshore drilling, like British Petroleum, or Exxon Mobil offshore drilling in the Gulf or close to Alaska in the Bering Sea. All of what is involved to bring it mainland, refine it, and render it ready to be used in a gas station, in a pump. What you do thereafter is beyond the control of whether it's BP or Shell or Exxon. So they would say well to wheel. So these are different abbreviated boundaries.